So in the previous class, I had given this problem, right? So anyone tried to solve this? Anyone tried? Okay. So we'll try to solve this problem. Right? So if the problems are given something like this, okay. So first step is what we had assumed that, or what, how to solve that. So you can either apply the loop current method or the nodal analysis, or sometimes we have to use the source transformation methods. Okay. Right. So let us assume that this is I1 current. So this is I1 current and this is I2 current, right? Okay. So now we will apply KVL in loop 1. If we apply KVL in loop 1, so what is the first equation? So how we will write the inductance value? How to write this inductance value? How to write this inductance value? Anyone?
L into dA by dt.
Yeah, L into di by dt, right? So that is L into di by dt. So this is L. If we assume that the current is flowing like this, so 2 into di1 by dt, right? Agree? So this is the current that is flowing, right? So 2 into di1 by dt. Agree?
Yes, sir.
Okay. So this plus, what is the second term? What is the second term?
1 into I.
Plus I1.
1 into I1.
1 into I1, right? 1 into I1 plus, what is the next term? 2 into I1 minus
I1.
I2. Agree? Okay. So what is the sign of this voltage source? What is the sign of this voltage source?
Positive or this.
So is equal to minus 2Vx.
Minus 2 Vx. So what is the second equation? What is the second equation? So it is, what is the second equation? 2 into I2 minus I1. All right. Plus 6 into I2, which is equal to 2 into Vx. Agree? Agree?
Yes, sir.
So now, if we add these two equations, right, or if you subtract the, if you subtract these two equations, in other words, if you write 2Vx in terms of this 2Vx can be replaced with minus of 2 into I2 minus I1 plus 6 into I2, right? Agree?
Yes, sir.
Okay. So our ultimate thing is to find out the current response in the inductor, right? So that means the inductor current, if you assume that, what is the inductor current? So what is I? Inductor current I. So this is equal to minus I1, right?
Yes, sir.
Yes, sir.
Okay. So what we have to do is we need to write the equations, right? Or we need to we need to develop the differential equations in terms of I1. We need to develop the differential equations in terms of I1, right? So that is the thing we need to do, right? So now, so what is the equations? If you write this in differential equations, so what is the final equations you will get? So how do we do this? Right. So what are the equations you will get? To simplify this one, so what equations you will get? So will it be 2 into
Sir, in place of
2
Vx,
by
we should
dt
write 1 into I1 now, sir.
1 into I1 only
plus I1 plus 6I2 equal to 0.
plus I1 plus 6I2 equal to 0. In other words, if you write the KVL equations to the outer loop, so that gives you the, if you remember that how you solve by using super mesh, right? So right, if you remember, if you solve by using this outer loop, so that gives you the same expression, right? That gives you this expression only.
Sir.
Okay. So from this, right? So from this, so what is the next step? So here this I2, so this I2 term is existed, right? So this I2 term is existed. So now, so what is the equivalent of I2? So that we need to find out, right? So can you find out? So what is the equivalent of I2?
Sir, can we write Vx is equal to I1, no, sir?
Yeah,
Directly.
Vx equal to I1.
Sir, then I2 is equals to I1 by 2.
Why?
Sir, from second equation. 2
From
into
second
I2 minus
equation,
I2 is equals to I1 by 2.
I2 equal to I1 by 2. So now substitute, what you will get? So this equation is di1 by dt plus I1 plus 6 into I2. So I2 equal to I1 by 2. So that means you're saying that 3I1, which is equal to 0. So that means 2I1 by dt plus 4I1, which is equal to 0. Is this the thing? Understood? So this is equal to 2 into, what is its value, Vx? What is Vx value?
I1, sir.
I1, right? Okay. So from this, you obtain this. Okay. Our ultimate aim is to eliminate I2 in this. Right. So this is the final expression, right? So this is the final equation. So this can be written as di1 by dt plus 2 into I1, which is equal to 0. Agree? Agree.
Yes.
So what are the limits for this integration? So next thing is we need to integrate this circuit, right? So one side you have di1 by dt, or other words, we'll rearrange the terms if you are confused with. So how to rearrange this one? di1 by I1, I will write in the next page, di1 by dt plus 2I1, which is equal to 0, right? So this can be written as di1 by I1. So what is on left hand side? What you will get on the left hand side? Minus 2 dt. Agree? Agree?
Yes, sir.
Minus 2 dt, right? So if we integrate this one, right? If this is 0 and this is t, so what is the value here? At 0
7.
time?
7.
Sure.
-7.
Minus
Yeah,
7.
that is true.
Minus
Why minus 7?
I1 is equals to minus I.
Yeah, I1 equal to minus, 1 second, the screen is freezed. One second, the screen is freezed. So take minus, so I1 will be minus 7, right? So from that, do it. So what you will get?
So 7 into e power minus 2t ampere.
Yeah. 1 second. Okay. So what is this value? This value is -7, right? Everyone understood, right? Why it is -7?
Yes,
So
sir.
this
I is
value
equal to
is-
minus I1, sir. That's
So this value is what you will get here, I1 of t, right?
yes, sir.
So what is I1 of t? How much you got?
Sir, 1 by 7 e power minus 2t, sir.
1/7.
Yes,
Minus
sir.
7 to e power minus 2t.
-7, right?
No,
-7
sir.
t to the power
It's -7.
t to the power minus 2t.
2 sir. Yes, sir.
Okay. So now tell me what is I1? I1 is
7 into e power
to the
minus 2t.
minus 2t amperes. So what is the next? There is another question in that, right? What is that? Vx, I think. What is Vx?
I1 only, sir.
What is Vx?
Vx equal to I1, sir.
Why I1? Is it minus I1, right?
Sir, this is I, sir.
This is-
7 into e power minus
That is I,
2t.
sir. I is equal to 7 e power minus 2t, sir.
This is I. So what is Vx?
I1.
Minus 7.
I1.
I1, right? So that's -7 into e to the power of minus 2t amperes. Okay, these are the answers. One is the current to the inductor. This is all for t greater than or equal to 0. This is all for t greater than or equal to 0.
That Vx is equal in
Sir, here will be volt, no, sir.
Yeah, it's in volts. Okay. Understood? Right. So how to solve these problems? Right. So first thing is we need to obtain the differential equation of the inductor current. Right. We need to obtain the differential equation of inductor current. So from that, by integrating that, so you can do the rest of the things. Okay. So I will give you one more example. Say it is 40 ohm. Six Henry, and this is 10 ohm. Okay. If I of 0, right? If I of 0 is 6 amperes, find I of t for t greater than or equal to 0. For t greater than or equal to 0. How to solve these kind of problems? How to solve?
Super mesh.
Why super mesh?
Nodal analysis, sir.
nodal, sir.
Why nodal analysis?
Yes, sir.
Because
Sir,
current source is there, sir. We cannot use KVL.
KVL only, sir.
Why? Can you see the circuit properly?
So we can't use it, sir, because we need to use we need to like not consider the branch like 0.5 current one, sir. We have to.
Just see the circuit properly and tell me. So what is the appropriate method? See this one.
KVL, sir.
Sure. So we have one current source is there, right? And see this one. Can we do anything with this?
Sir, that
Sir,
is
we can convert into equivalent voltage, sir.
Yeah, you can
Voltage.
convert this into an equivalent voltage source, right? If thing is that if you convert this into equivalent source, so one loop is reduced, right? If you convert here two loops, right? If you convert this into voltage source, you have only one loop. So, okay. So from that, you can solve it. Understood? Okay. So from that, you can solve it, right? If you solve that,
Could-
so I will
So could you
provide the
repeat,
answer.
sir?
Yes.
Could you repeat? I don't understand.
So we have current source is there, right? Okay, this is a practical current source. So this current source can be converted into a practical voltage source. We discussed this, right? So convert this
So
into
we are,
practical voltage
so
source.
we are basically eliminating this loop and we are going to consider it as a voltage source.
So it will be like this, right? So this is its equivalent current source, this and this portion. So this is
Yes,
10 ohm. So this is 6 Henry. What is this value?
uh,
So 20
Why
I.
20?
40,
So this is 40 ohm only, right? So here, what is the symbols? So this is
20
minus
I.
here and this is plus, right? So this is 20I. Okay. So this is the inductor current is already given, right? So assume that this current is I. So formulate the differential equation. So from that you calculate the I of t. So it will be 6 into e to the power of minus.
Sir, plus minus, sir, that voltage source.
Why plus minus?
Sir, it is pointing downward, no, sir.
Yeah, downward is the arrow head is plus, right?
Arrowhead is positive,
The
sir.
arrow is positive and this is negative. That is the first thing, basic thing we require, we learned, right? Okay. Understood? Okay, if you solve this one, so you will get this output. Okay, so shall we move to the next topic? You have any questions in this?
Sir, or instead of converting that current source into a voltage source, we can divide current and consider a loop and do it. No?
That will complicate, no? You will get the answer.
Means 0.58 is going here, no sir. 0.58 through 41.
So how do we
resistor
convert
and
this one?
converting
How do
loop
we
lamp.
convert through the 6 Henry resistor, 6 Henry inductor? So there is a 6 Henry inductor is also there, no? How do we convert that?
No sir, dividing current 0.58 and 40 ohm resistor 0.58 and using loop law for that one.
Maybe you'll get the answer. Okay, that's not necessary. Okay,
Yes sir.
but there are several methods are there, no? This is one of the method, or else you can use the super mesh, right? By using this, circulating this, maybe you may get the answer also. So next thing is, so far we discussed about the natural response of series RL and RC circuits, right? So next we move to the other topic. So that is the forced response. Forced response of RC circuit. What is the forced response means? The circuit is energized with source. The circuit is energized with source. So let us consider a simple circuit, something like this. Again, we'll start with RC circuit first, and later we'll go for RL circuit. So let's say this voltage is Vs, and this is R, and this is C, right? So now assume that the switch is closed at t equal to 0. At t equal to 0, the switch is closed, and this is the voltage across the capacitor. Voltage across the capacitor. And also assume that voltage across capacitor, right? So which is equal to V0. So initially the capacitor is charged to V0. Okay. So initially assume that the capacitor is charged to V0 with some external circuit, right? So how it is charging, so that is not important for us. The thing is that the capacitor somehow this capacitor charged to V0 voltage, right? So one side you have Vs and other side, so that means already capacitor is pre-charged with V0 voltage, right? So earlier there is no source, right? So now the t is equal to 0, the switch is closed, right? For t greater than or equal to 0. So what is the equivalent circuit? So this will be the equivalent circuit, right? Okay. So this is the equivalent circuit for t greater than 0 since the switch is closed. So assume that this current is I. So assume that this current is I. Right. So what is the current through this inductor, or what is the current through this capacitor? If this is I, what is the current through this capacitor? What is the current through capacitor? If you know the voltage, what is the current through capacitor?
C into dv by dt.
C into
dv
dV by dt, right?
dt.
What is the current through resistor? If you know the both voltages, what is the current through resistor? What is the
Vs
current
minus
here?
V.
So Vs
Vs
minus
minus V
Vs
of R.
minus V by R, right? So wait, Vs minus V by R. If you notice that I have written lowercase letters for this V. Why it is V? Because it's time varying, whereas the source is independent of time, right? So that's why I used the capital letters. Okay, so this is the current. So here there are two possible ways to represent the current, right? So one is the resistor current or the capacitor current. Since it is a series connection, so both are same. Okay, so now we'll try to rearrange these terms, right? We'll try to rearrange these terms. As why we are rearranging these terms? Because we are interested in finding out the voltage across the capacitor, right? So can we write like this? dV by, right, dV by what we say, if you move this one to this side, Vs minus V, okay, equal to, if you take this one from this side, dt by RC. Is this correct?
Yes, sir.
Okay. Right. Is this correct? If you notice that it is Vs minus V, right? Okay, it is Vs minus V. So our thing is that we are interested in this voltage, right? So therefore, I slightly modify this one. So dV by V minus Vs, which is equal to minus dt by RC. This is the correct representation, right? Agree? I just multiplied with minus 1. Why? Because it's Vs minus V. Again, when you're integrating that, you will get minus terms. To avoid that confusion, I just modified these terms. Understood? What is the next step? What is the next step? Integration, right? So integrate this one. So dV by V minus Vs integration minus dt by RC. What are the limits here? So its limits are 0 to t. What are the limits here? What are the limits of capacitor voltage?
V naught.
V
V
naught
naught
to
V of
Yes.
V?
V is the
Why
function of
Vs?
T.
V of t, right?
VT.
V of t only. Vt or V of t? V of t, right? Understood? So our
V of t.
objective is to find the capacitor voltage for t greater than 0, right? That is the thing, right? If t is the time, so this is V of t. So now integrate this one. So what you will get, ln, right? What is the first term? ln into V of t minus Vs. Correct me if I'm wrong. Okay. Minus ln into, what is the next term?
V minus
V naught minus
V naught.
Vs.
V naught minus Vs.
Okay. Equal to minus t by RC. Agree? Understood?
What is that Vs, sir?
What is that Vs? Vs is the source voltage, no? That is the one you are talking about.
Sir,
Yes.
Sir, what exactly does forced response, sir, mean?
Forced response means earlier we have natural response, right? So that means see here for RC circuits that there is when it is discharging, the simply whatever the stored energy in the capacitor that is discharging through the resistor, right? Okay. So now thing
Yes.
is that so one time see here there are now the capacitor there are two, right? There is internal energy is there and also some energy source which is also constantly pumping the energy. So that means the capacitor is also excited with some internal energy. So now how it will respond, so that we are going to find out. Okay.
Yes, sir.
So previous case, if you notice that see here circuit something like this, we have formulated this. See, this is the circuit, right? So what, see this circuit is not energized, right? So for t greater than or equal to 0, the circuit is not energized. So whatever the internal energy or what is the energy stored in the capacitor, that is dissipated in the resistor, right? So now what we are doing is forced response is, so here this is also containing some internal energy or some initial energy. That is one thing. And another thing is we are trying to charge the capacitor. We are trying to charge the capacitor with some external circuit or with some external source or with some external force. So we are doing that two ways. So one is we have internal energy stored in the capacitor. So that is one thing. Another thing is we are trying to charge the capacitor. So when we have internal energy in the capacitor. So that is the thing. So this is the circuit, right? So now if you write this one, V of t minus Vs by V naught minus Vs equal to e to the power of minus t by RC, right? Agree? Okay. So from this, what is V of t? What is V of t?
Vs plus V naught minus Vs into e power minus t by RC.
Vs plus
Not minus
t
Vs.
V naught minus Vs into e
V
power minus
naught
t by RC.
minus Vs
Vs
to e to the power of
into e
minus
power
t
minus t
by
by RC.
RC. Right. So this is the response of the capacitor when we try to charge the capacitor, when we try to charge the capacitor with Vs source, and it is having some internal voltage which is equal to V naught. Okay. Right. So that means what ultimately we got is V of t, so which is equal to Vs plus V naught minus Vs into e to the power of minus t by RC. Okay. Understood. For V infinite time, so what is this value? For infinite
Yes.
time, so what is this
Yes.
value?
Vs.
Yes, sir.
So its value is equal
Yes.
to Vs, right? Everyone
Vs.
agree for that, right? Its value is Vs. At V equal to 0 time, what is this value?
V naught.
So it's Vs plus V naught minus Vs, which is equal to V naught. Right. Thing is that, so this will be its initial value and this will be its final value. So how exactly that is reaching to its final value? So we have t here, so 0 here. So how to draw this curve? So somewhere we have this V naught, right? Somewhere we have V naught. So how it will changing? So how exactly it is moving to this Vs? It is exponentially changing, right? It is exponentially changing. So there are two possibilities. If this V naught is less than Vs or V naught is greater than Vs. If this is the case, right? If this is the case, somewhere you have Vs is there. So that means it will exponentially increase it to Vs. Agree? Agree for this?
Yes, sir.
Yes,
So
sir.
this is first case. or I will write here. So when V naught less than Vs, so there is another possibility that it will be less than that. So it will be like this. So this is Vs. So this is for V naught greater than Vs. Understood? Understood. What is the difference in previous case and this case? When previous case, right? So when previous case, what happened is whatever the stored energy in the voltage, if you notice that if you compare with the previous case, so this is V naught, so this is 10 to 0. So that voltage is 10 to 0. So now what's happening is now it is moving to, or now the capacitor charging to the whatever the source we are connected. So that voltage, that is Vs. Now the capacitor charged to Vs voltage. Understood? Understood.
Sir.
Yes, you have any questions? We have any questions? So here also we can define the time constant. Okay. So we can define the time
Sir, if the
constant.
V naught is 0, graph in the fourth quadrant.
V naught is 0.
Graph in the fourth quadrant.
No, good question. For example, V naught is 0, right? So how the graph will go? So this is T, right? So V naught is 0. So this is V of T we're drawing. So what is its final value is Vs, right? So how it will increase? So it will increase like this. That's all. It will not go to the fourth quadrant. This is the graph, right? And V naught equal to 0. If substitute that in this expression, V of T, right? If V naught equal to 0, so what is the expression you got? So it's Vs into 1 minus e to the power of minus T by RC, right? Agree? Agree?
Yes, sir.
Okay. So this is for V infinite at V naught equal to 0. What is its final steady state value? What is this value? It is infinite.
Yes, sir.
The value is
Yes.
Vs, right? Okay. Same thing at V of 0 at V naught equal to 0. So its value is 0. So that means it starts from 0 and it reaches its final steady state value Vs. Okay. Understood.
Could you repeat the point again, sir?
It will start from 0 and it will reach its final steady state value Vs. Right. There are two possibilities. So one, the capacitor is charged with initial voltage. Right. So in that
Okay.
case, it start from origin and it will reach the final steady state value. So Vs. Okay. So that is one thing. So another aspect is that so capacitor is having some initial voltage V naught. So based on that initial voltage, the final value is Vs. This final value is Vs. So how to reach this Vs? Again, there are two possibilities. So there is one case V naught is less than Vs. So in that case, this is the possibility. And case V naught is greater than Vs, and this is the possibility.
Yes,
Understood?
Sir. Yes, sir.
So this is how it will reach its final steady state value. So thing is that its initial value is V naught and its final value is Vs.
Yes, sir.
Right. So now how to define the time constant in this particular case? In this particular case, how to define the time constant here? So what is its final steady state value?
Vs.
So here it's okay. So how to define its final? This is from 0 to, right? So here the response is reached to 1 by E of its final steady state value, right?
Sir.
Yes, sir.
So here what is the final value here? So at what period we calculate its final steady state value or this value? At what point we will calculate? So now how do you define its steady state value? So how do we
Sir,
define it? Oh,
Sir, in the middle graph, sir, I'm not understand why Vs and above Vs and below Vs of V naught.
this one. Hmm?
Yes, sir. On y-axis.
Yeah, this one only. There are two possibilities, right? What is there? Let us
Sir,
assume
but
that we'll talk about the
from
network.
reference 0.
Sir, let us assume that this is 10 volts, right? Okay, initial voltage is V naught is 10 volts. So there are two possibilities. If Vs equal to 15 volts, for example, so Vs is 15 volts,
Yes, sir.
right? So that means from t equal to 0, its value is 10. At t equal to infinite, its value is 15. So how do you draw the curve? So this is the curve, right? Agree? So this is the
Yes, sir.
curve. So there is another possibility that so Vs is equal to 7 volts, or for example 5 volts. So here you have 5 volts and here you have 15 volts. So how you draw the curve? So this is the one, right?
Okay, sir.
Okay. So here there is only one thing is correct. Either you have 15 or 5 volts. I'm just illustrating that. So obviously there are two possibilities, right? So one is the greater than the initial voltage or lesser than the initial voltage, the source voltage. Okay. So here also the time constant, so tau equal to RC. So RC is the time constant in this case also. So therefore this equation can be written as V of t can be written as Vs plus V naught minus Vs into e to the power of minus t by tau. So where tau is the RC or R equivalent into C, so which is time constant. Right. So these equations can be written in other forms, right? In different forms. So this V of t, if you add this one, so first one is Vs, if you take Vs common, so one is 1 into e to the power of minus t by tau, agree? So what is the other term you left? V naught into e to the power of minus t by tau. Is this correct?
Yes, sir.
Is this correct? So if you notice that what is this one? So this will be the natural response, right?
Yes, sir.
Agree?
Yes, sir.
So this will be the natural response and this one will be the forced response.
Should response.
So this is due to the excitation voltage Vs and this is due to the internal voltage or voltage across the capacitor V naught. Okay. So that means the final response. So this is the final response. So final response equal to forced response plus natural response. Forced response plus natural response. Understood? Right? So can we generalize this one? If we generalize this equation, so this V of t. So what is Vs? So Vs is its steady state value, right? So this can be written as V infinite, agree?
Yes, sir.
Plus what is V of V0? So which is equal to V0 minus V infinite into e to the power of minus t by tau. So this is V infinite plus V0, V of t. So that means its final steady state value, and this is initial value. Okay. Final value and that is initial value. So this can be written as final value plus initial value minus final value into e to the power of minus t by tau. Right? So this is very important. So most of the problems, so we have to use or we have to rely on this formula only. So final value plus initial value minus final value into e to the power of minus t by tau. So we'll try to solve some problems. Yeah. Understood? Right. So if you remember these equations, you can remember anything, right? Okay. So next thing is we'll try to solve one workout example. So this is 7.5 volts. Okay, so this is 6 ohm. This is 1/3 farad plus minus V. So this is 15 volts and this is 2 ohm. And the switch is closed at t equal to 0 seconds. So what we have to calculate? So calculate V of t per. So calculate V of 0.5 value at 0.5 seconds. So we need to calculate what is V of what is voltage across capacitor. All right. Okay. So what is the first step we need to do? What is the first step?
So calculate V naught.
Yeah, calculate V naught. So how to calculate V naught? How to calculate V naught?
The left part of the circuit.
If you notice that at t equal to 0 only the switch is closed. So that means before that time, so the circuit is energized, right, for a long time. So now tell me what is the voltage across the capacitor?
15 volts, sir.
volts.
15 volts.
15 volts.
So 15
It's
volt.
simple, right?
15 volts, sir.
15 volts. Voltage across the capacitor from this circuit. So voltage across the capacitor is 15 volts. The capacitor is charged to 15 volts. Right. What is the next step? So we need to draw this circuit. So this is for t greater than or equal to 0, right? Agree? Agree?
Yes, sir.
So next step is how do we calculate or how we calculate the what we say? How we calculate the
VS, sir.
capacitor voltage
Yes.
V, or in other words V infinite or final value. How we calculate this V infinite value or final value of the capacitor?
Final
Capacitor
stage
will behave as a,
will break the
as a
circuit.
short circuit, sir.
Capacitor is behave like a wire, sir. We can remove
Short
it.
circuit. We can remove it, sir.
If it is short circuit, why we have to remove that?
Open circuit, na sir?
Sir, it
Keep
will be open
circuit,
circuit,
right?
sir.
Open
That
circuit.
means the circuit will be something like this. So this is 7.5 volts and this is 6 ohm and this is 2 ohm and this is 15 ohms. Our objective is to find out this voltage V. Agree? So how to find that voltage? How to
So
find
first
that
we'll
voltage?
find the overall current, sir, and then sir we'll
You find the
multiply.
overall current. If this is overall current, right? So what is I here? Okay, I have to use lower case letters. No? This is V and this is I. So what is I here? What is I?
22.5
So
on it.
2.5 by 8.
22.5 by 8. So what is this value?
2.8, sir.
2.8 exact. 2.81 I think.
2.812.
I already told no, you have to do with at least 3 digits from the point. Okay. 2.812 amperes, right? So now
Yes,
what
sir.
is this voltage V? What is this voltage V? It will be 15 minus
15 minus 2
2
into.
into I, right? Agree?
Yes, sir.
Yes, sir.
15 minus 2 into I. Agree? If this is plus minus. Agree? So what is this voltage V?
9.37. 9.38.
9.372.
37.
5.
So 2.
378, sir. 378.
Okay, anyway, 9.375, I think someone told. Anyway, that's. So this is volts, right? So this is its final value. Agree? Agree?
Yes, sir.
Yes, sir.
So next step, so this is its final value. So that means V infinite is 9.375. What else we required in the formula? What is the answer? V of t equal to V infinite plus
V infinite
V0
minus V naught, sir.
minus V in at rank e to the power of
Minus T about
Minus T by RC.
tau,
RC,
right?
sir.
What is tau
Not T by
here?
T.
R
What is
equivalent.
tau?
5 point.
How to calculate tau?
2 by
R
3, sir.
equivalent.
R equivalent into capacitance. R equivalent is 2, no, sir.
Why R equivalent is 2?
Sir, tau point.
Equivalent is 3 by 2, sir.
Sir,
3.2. R equivalent.
sir 1.5 are equivalent.
How to calculate R equivalent in this particular cases? Hmm?
R equivalent across capacitor.
R equivalent across capacitor.
How to
6 and 2 will
calculate
be
that?
in parallel.
6
No,
into
sir.
1 parallel, sir. 6 into 2
6
by
and
6
2 are
plus.
parallel.
Not the batteries.
3 by 2.
3 by 2, sir. Yeah.
3 by 2. See, remember, if you want to calculate the equivalent resistors, so there is a method, right? So here, so when you have the voltage sources, short circuit the voltage sources, right? When you have the current sources, open circuit the current sources, right? For this, if you do like this, if you have voltage source is there, right? So short circuit that. If you are here, so one capacitor here, and another voltage source is there, short circuit this one. Okay, so this is C and this is 2 ohm and this is 6 ohm, right? So now the 6 2 R in pair, this is C is 1.3, right? So from this, calculate the value of RC. What is the value of R equivalent C?
1 by 2.
R equivalent of C is 1 by 2. Okay? So
Yes,
that
sir.
is how we calculate the time constant in slightly complex circuit. Okay. The first thing is short circuit the current sources, whatever the current sources is there, right? This is current source. So short circuit this one. So this is also short circuit this. If you have a voltage, if you have short circuit the voltage sources and open circuit the current source. For example, you have an open voltage source is there, right? Or some current source is there. You just open circuit that or ignore that circuit. So that is how we will find out the R equivalent. Okay, so that we will find out how we, that is how we will find out the R equivalent. Understood? So from this circuit, R equivalent or tau equal to 1 by 2C. So now tell me what is the final response? So what is 9.375
375
plus
plus
VF0? What is VF0? 15, right? So 15 minus 0.93 975, right? E to the power of minus t by 1 by 2 minus 2t amperes, right? Agree?
So 9.375.
9 point, okay, this 9.375. So now what is V of t? 9.375 plus 15 minus 9.35, I think 5.625
Yes, sir.
e to the power of minus 2t amperes. So what is, no, this is not V, oh, no,
Volt,
this is
volt.
V of t. This is volts only. All are volts only. Here also these are volts. So V, what is the question? V of 0.5, right? So substitute 0.5 over there and tell me the answer.
So 11.44 volt.
11.44. Its value is 11.44. 11.44. So what you understood that its initial value is 15 volts. From 15 volts, it is moving to 9.375. That is its final value, right? From 15 to its final value is 9.375. So from here, and during that path at 0.5 seconds, so this is its value. Understood? During 0.5 seconds, its value is 11.44. Its journey started at 15 volts and its end value is 9.375, right? So in between at 0.5 seconds, so it touched the 11.44 volts. That is its meaning. Okay. So things you need to remember is, so this is the formula you need to remember or you need to understand. Another thing is how to calculate the time constant in a complex circuit, right? If you encounter a voltage source, short circuit that voltage source, and if you encounter a current source, open circuit that, right? And deduce the circuit, something like this. This is the circuit is deduced to calculate the R equivalent into C 1 by 2. Okay. Clear?
Sir,
Yes.
sir, why do we do open circuit and current source, sir?
That we'll discuss in one class. Okay. Just remember this much for time being.
Okay, sir.
Actually, you're supposed to learn that there is one theorem is called Thevenin's theorem. Okay, and that is there. Based on that, we are calculating these things. That thing, you have another course on the circuit theory. No, this is part 1. So there is another one. So that is part 2. So in that you will learn the things. Okay.
Okay, sir.
We'll discuss the anyway. No problem. If your time is less, that's why I'm not discussing. Just remember that we need to open circuit the volt current source and short circuit the voltage source. That's the thing. Okay, any questions on today's class?